Good morning. My name is Fazia Faria. Today, I'm going to present nearest neighbor algorithm. We have named our project Speeding Up Spatial Searches. So I have been assigned task one, and this task has given me the restaurant dataset. So we will go over the dataset and then we will go through three methods. First one being the sequential, which we also call the baseline method. Then we will go over R-tree, where we will introduce the MBR. Then we will talk about the divide and conquer, where it divides a line in the middle, and then we will analyze the performance of the three methods. So the goal is to find the nearest restaurant for each user. So about the data sets, I've received two. One was the restaurant data set, which had 150,000 points, and the other one was the query data set, which was the user query points. Both of them had ID and X and Y being geographical location. So we will perform the nearest neighbor algorithm of these three methods, and they will give us the restaurant, which is the nearest, and also the total time taken to compute that result. So why this matters in real world is when, for example, I want to book an Uber. Uber will direct me to a driver who is in close proximity to me. So that is how the spatial searching actually works. So first one we will go over is the sequential scan. As we mentioned, it's the baseline method. It's the most simplest one. It starts a query and then it checks every facility and then it gives us the smallest distance. So the sequential scan actually uses the Euclidean distance to determine the facility. And here, as we have established that we have 200 query points and 150,000 points in the restaurants, we will actually go over this one by one. So 200 queries against 150,000 restaurants. So going back to Euclidean distance is basically a straight line between 2 points in 2D space, which is used by the X and Y coordinates. This is a standard metric in the nearest neighbor search. Next, we move on to the R-tree. Now, the R-tree actually reduces the amount of Euclidean distance checks we have to do to perform. As you can see, here is an inefficient graph, and this is an efficient one. So why the difference is because here it's actually grouped into rectangles. So when it is grouped, it actually minimizes the overlap. So over here, it's too big of a chunk. So I will talk about the MBRs. So the MBRs is basically minimum bounding rectangles. So what it does is it groups the nearby points into rectangles. So as you can see here, there's one MBRs, here's another one, and this is our query point. So in spatial index theory, grouping actually improves efficiency, and that's what the R-tree does. And it also prunes. So pruning is when a bounding rectangle is very far from the query point. For example, this one, it's too far. Then it just automatically skips that rectangle altogether. And that skipping behavior is what they call pruning, and the branch and bound strategy uses it best. So it's because it works with the distance, the best distance it has found so far. So as the data set increases, it will add more points and more rectangles will be built. So what it does is if it finds another rectangle whose distance is way worse than the current one, then it just skips that one. So due to this, fewer mathematical operations take place, and in big data, reducing the number of distance calculations is actually a really good achievement. So, and also in spatial index theory, this is widely used in logistics, in mapping, in ride sharing, etc. So why did we use R-tree? R-tree, again, as it gets efficient, it groups everything, and it actually narrows the search rather than going through each and every point. So that actually saves a lot of time, and they do that with the help of MBRs. So this results in fewer nodes getting visited, and it works very well on large data sets because as the points and it keeps growing, it works better, and those points and the rectangles get added to the hierarchy. Next, we will look into divide and conquer. This one, in my opinion, I found it a little interesting. So it actually divides the map into two halves. So they go through the first half, and then they move on to the second half. And it's divided in the x coordinate, and we call this line L. Let's call this line L. And it treats each side as two different problems rather than one big chunk of messy data. And I thought that was a little interesting. So this actually reduces time by checking points and by checking the points which is nearer, and that cuts down the time in checking. And this method is what they call working smarter, not harder. And it balances the search in a very smart way. So if we talk about closest pairs, so first, as we've established the line L, after it divides it into two halves, now it starts to look for closest pairs. So first it finds a closest pair, for example, on the left side. So as it always starts one side, and then if that's good, and then they move on to the other side if needed. So for example, right now they found a closest pair on this side. So the closest pair would be the ones that are very close to each other. And they find another one on this side. So it would be two candidates on both the sides. So the smaller of those two distances, so the smaller of the two distances, for example, if I can call these two a pair, the smallest distance, or the smallest distance is what they call the R. So the point of focus is, instead of searching everywhere all over again, it focuses on points that fall within this line, and it's it's closest to the closest pairs. So the next, we will talk about our performance on the three methods. So the sequential scan being the simplest one, it has given us a very small runtime. You can see that it was pretty fast. Maybe it can look like it was really good. However, it can collapse when the data gets bigger as it goes through each and every point. And it's definitely always accurate all the time, which is why it's used as a baseline, and the results are used to compare with other algorithms. And the result of the R-tree has been 1.78 seconds, which has been the most efficient and is actually a winner for our case. And divide and conquer has actually taken the most time. This could be because of the overhead costs, or the all that task where you have to divide, then check the points, and due to all of those procedures, this can get time consuming and also expensive. So I think that was the reason why it didn't perform so well in our data set. Now, to conclude, I would say sequential scan is definitely simple, but can be inefficient because it only works with large data sets. Then we have the divide and conquer, where it does extra work. It does a lot of extra work by dividing the line. And even though theoretically it can seem efficient, but it for our task, it didn't do what we anticipated it would, because I personally was assuming that the sequential scan would take the longest time. However, as our data set was not very large, it gave us the opposite result. And we can conclude that R3 provides the best real world speed due to its pruning and grouping, and it's very, very efficient in real world when we are either ordering food or ordering a cab. We want the results, or even when we are looking for a nearest cafe, we want the results in real time. And R3 is really effective in that, because as the data set grows, it has the ability to adapt and fit in with a real world scenario. And obviously, it's because of its pruning. And the last one would be, yes, all the three methods have returned identical result. I may have not mentioned it at the beginning of my agenda, but we wanted to see if all the three methods have returned the same result, and it did. And the difference in their results is mainly on how much unnecessary work each method is actually avoiding. So with that, thank you so much for listening.
All right. Good day, everyone. My name is John Lloyd Nashon, and I'm here to present to you our task two. It focuses on implementing skyline algorithms to be used in a multidimensional data, which is in this case the ct1.text, because our modulo was 0 when we added all our student ID numbers last digit. And yeah, so basically, let's get straight into it. So first, for our agenda, I'll walk you guys through our dataset overview, and then next we'll discuss each algorithm. Firstly, with sequential scan. Next is with the BBS R3, or branch and bound, and lastly is the divide and conquer. Then I just summarize you throughout the whole process of the task 2, and we'll compare each algorithm results and get the necessary insights and conclusion about it. Alright, so for the first one, our dataset name is city1.text. It contains over 30,000 records, and each record has three main attributes. So first is the ID, next is the cost for X, and Y is for the price per square meter. So the aim of this task is basically to get the lower total unit cost and the lower uh, unit price per square meter cost. So as you can see, the scatter plot, it just shows that a downward trend since we're looking for the the lower cost. So this is just a simple overview of how the data set works. So as you can see, the blue one are all the dominated points, while the red one are the skyline points, or what we call the non-dominated points. Right, so for the first algorithm, we choose, or we're using sequential scan. So this is just the baseline skyline algorithm. So basically, it compares every data point against all other points. So basically, for the 30,000 records, we're just checking for each point to the all others. So it can be te technically slow because it doesn't work really well or efficiently with large data set because in essence, it's basically like checking the tallest person in a city, and we if we don't like if we don't what do you call this uh mer- merge them with to each neighborhood, it can be very slow when we're comparing it to the whole city. So basically, the whole process is just inputting the data set, and then we do a pairwise comparison, and then we just for the output we choose the non-dominated points. Right. Next is the branch and bound skyline with R3. So this improves skyline search using an R3 index to organize data into smaller regions instead of comparing all points one by one. So it uses nodes. So the root node is the entire city dataset, city one, and then it it chooses the relevant node, which is in this case, what we're looking for is the lower total cost, unit cost, and lower total price per square meter cost. So in essence, as you can see, the red ones are in the leaf are in the internal node A, which is the low cost, and there's also another red in the medium cost, but there is no skyline point or red one in the high cost because it's not relevant to the what we're looking for. So basically, in this case, the leaf one, there's two skyline kept, and then next is the medium, which were some mixed, and the high cost were entirely skipped. So that's why it's more efficient because it entirely skips the nodes that are not relevant. All right. Lastly is the divide and conquer. So this also uses R3 because in essence the difference is it just divides into two sections. So in the middle it divides, and that's where we check for the skyline points, which is again in the low cost and the medium cost. And then if after all that we're gonna merge it into a local one, and then we're gonna remove the dominated points, and of course the final output are the same for all skyline algorithm. It's about 5 points. Those are the skyline points, and it also shows the execution time, the speed of how algorithm each algorithm works. So to summarize, so this is the overall task 2 process. So first is the input for the dataset, which contains 30,000 records with three attributes, and then we use for each and every algorithm. For the first is the baseline, the sequential scan, and then the index search, which is the BBS with R3, and the parallelized search, which is the divide and conquer. And then next is display it into the output to that text file, which is it shows the non-dominated points or the skylight points, and then their execution time comparison to each. All right, so these were the results. So as you can see, the slowest was the sequential scan because it was the just a simplest method out of the three, but it can be very slow or relatively slow to a large data set. Whereas the branch and bound skyline and the divide and conquer were faster for specifically for BBS where it was 1.67 times faster than the sequential scan, and the divide and conquer was 1.20 faster. So as you can see, this BBS was the fastest. Then in conclusion, all three algorithms were just the same 5 skyline points, confirming consistency, and the sequential scan serve as a baseline. So because it requires the most pairwise dominance checks, it can limit their scalability for the dataset. And the BBS achieved the fastest runtime with 1.67 faster than the baseline because of its pruning the dominated region through its hierarchical search, and the divide and conquer approach a 1.20 times speed than the baseline, so it's also still effective. So in conclusion, uh, basically this one, like small data sets, it still works fine for the sequential scan, like because I've researched about that sequential scan really doesn't work with real life application of real life data set, because relatively this 30,000, it's huge, yes, but relative to the real world, it's little. So yeah, and for the of course for the larger data set, BBS and divide and conquer would scale better. So yeah, that's all. So that's for task two. I hope you enjoyed. In my part, I've enjoyed learning with this unit. It can be very technical and theoretical, but it's a lot of fun. So that's all. Thank you.
Good morning, everyone. My name is Mohammed Abdullah Malik, and I will be presenting Task 3, Project Report for our group assignment 2. My role in this task focused on verifying results, building the explanatory diagrams, and documenting the nearest neighbor and skyline algorithms. Our team divided the project into three major tasks. Task 1, which focused on the nearest neighbor search handled by Fozia. Task 2 implemented the skyline search led by Jay. And task 3, which I completed, covered the documentation, diagram creation, and analysis of algorithm performance. In this presentation, I will briefly explain the program environment and the documentation, and then go into detail on the diagram that visually explain how our algorithms work, which will be my main focus. All implementations were, keeping in mind of the program environment, all implementations were done in Python 3, executed on both Mac OS Monterey and Windows 11 for cross-platform verification. The allowed libraries, time, SYS, math, TQ, DM, NumPy were strictly followed. No external R-tree or spatial indexing libraries were used. Datasets such as restaurants.txt and city.txt were kept in a single directory. The programs ran efficiently with total runtime under 40 seconds and CPU usage below 60%, confirming the design was both accurate and efficient. The project was structured modularly, and keeping the documentation in mind, the main.py, like the main directory which was used was main.py, the nearest neighbor, r3.py for index structure, utils.py for helper function, and task algorithm.py for skyline search, and many more as you can see. And the main functions that we used were, as you can all see, these divide and conquer, skyline dataset, and all of these. I reviewed the document each module and focusing on how function interacted. This organizations helped me debug and understand the tasks as well. This is the R-tree structure built for the nearest neighbor search. At the top is the node U4, the root containing the three minimum bounding rectangles, R1, R2, and R3. Each MBR represents a leaf node below it that stores the actual data points. U1 holds P1, P2, P4, and P5. U2 holds P7 to P7, P8, P9, and P10. And U3 holds P3 and P6. The blue lines, show the parent-child links. This hierarchical grouping ensures that when searching for the nearest neighbor, the algorithm does not scan all points, but only the relevant rectangles. In short, the R-tree provides a foundation for efficient spatial queries. This diagram shows the branch and bound BAB algorithm in action. The query point Q is at 7 on x-axis and 6 on y-axis, shown by in the small circle. The algorithm starts from the root and computes the minimum distance between Q and the and each MBR, R1, R2, and R3. Since R2 is the closest to the to Q, the algorithm expands the region first, examining the points inside it, P7, P8, P9, and P10. It then finds that P8, which has the coordinates 6, 4, is as the nearest neighbor. The other rectangles R1 and R3 are skipped because their minimum possible distance is greater than the distance to PA. This shows how branch and bound significantly reduces comparison by pruning irrelevant regions instead of checking all points. Here we see the divide and conquer approach for the same nearest neighbor problem. The dataset is split along the vertical line shown in the middle, dividing points into two subsets: left region, which contains P1, P2, P3, P4, and P5, and the right region, which contains P6, P7, P8, P9, and up till P10. The Curie point Q falls on the coordinates 7 and 6. So as the Curie point falls in the right partition, so the algorithm searches that site first and finds P8 as the nearest point. The key advantage is that each subset can be processed in parallel or independently, making this method faster for a longer data set while maintaining accuracy. So now moving on to the skyline search, the R-tree structure is built on 15 points provided in TOS-T sample dataset, P1 to P15. As you can see, the leaf nodes U1 to U7, which are these ones, store the data points while intermediate nodes, while the intermediate nodes U8 to U10 group nearby regions into MBRS R1 to R7. This hierarchical and obviously the root node U11 is connects them through R8, R9, and R10. This hierarchical structure is essential for Skyline search because it lets the algorithm eliminate entire dominated regions early. For example, if an MBRS is dominated by another, none of its points need to be checked. This is the BBS algorithm process for Skyline search, branch and bound Skyline. One of the most important parts of the project, the root level rectangle R8, R9, and R10 represent the three main regions. The algorithm uses a priority queue based on mindsets from origin. Origin is basically where the Y and X lines that cross each other. That's the origin, which is coordinates of 0, 0, of course. So R8 is expanded first, and it's closest to the origin. As we expand nodes, dominated areas are pruned immediately. For instance, points in R10 such as P14 and P15 are dominated and skipped. After the entire process, the remaining non-dominant points are P3, P2, P8, P9, P12, and P13. This demonstrates how BBBS efficiently finds the skyline without needing to compare every pair of points. Finally, this figure shows the divide and conquer approach for Skyline. The vertical line divides the dataset into two subregions, left and right again. Each subregion computes its local skyline independently, shown by the step lines. Left skyline includes P3, P2, and P8. Right skyline includes P7, P9, P12, and P13. But when they're merged, we get the final skyline set as P3, P2, P8, P9, P12, and P13. Because each partition runs in parallel, this method reduces runtime by almost 40% compared to the sequential approach. So to summarize this performance, I would say that the BAB and BBS algorithm both showed significant speed gains through pruning and divide and conquer proof scalable for a larger data set. And to conclude this, I would say that TOS3 helped me connect theory to practice, especially in understanding how R-tree structure enhance spatial research efficiently. Through this analysis, I learned how indexing, pruning, and parallel processing combine to create high-performance algorithm. The report and diagram I prepared not only validated our group's implementation, but also provided a clear visual understanding of how these algorithms work internally. Thank you.